Thank you. Okay, so today we're going to spend some more time on the concept of oxidation levels. And if you remember, we said that organic chemists often tend to not give as much credence to oxidation number or oxidation state as the way we use them in inorganic chemistry, because oxidation states don't always give information that is accurate for organic chemistry. We talked about the case that even though the chemistry of CH4 and C2H6 is essentially identical, except for the kinetics, because this is 14 units heavier, the oxidation number of the carbon here, again, each H is +1, so that's +4, so the carbon here is -4, whereas in this species, this is +6, this is -6, so this is C4 minus, this is C3 minus, because the two carbons are collectively -6, so each one is -3. So what this suggests is that each of these carbons, there are different oxidation states, and this carbon in methane is more reduced than the carbons in ethane, which we know from the chemical behavior of these species, we know that's not true. But if we look at them in terms of oxidation level, which is the number of bonds the carbon has to heteroatoms, then both of these are at the same oxidation level. And if you look at the lecture beforehand, the lecture before this one, we had identified all of the oxidation levels, and so I'm just going to assume you've had a chance to look at those and you are familiar with them. If you are not, let me suggest we pause the lecture at this point and go back and look at the oxidation levels we looked at, the alkane level, alcohol level, aldehyde, acid, and carbon dioxide level, because that's critical to what we're going to do next. So what we'll do is I'm going to draw a couple of compounds on the board. We will go through them and identify oxidation levels so that we're familiar with it moving forward. So we could look at okay, so we're going to ask what are the oxidation levels of each of the carbons in this molecule. So let's start here. This carbon, right? This carbon has no bonds, has 0 bonds to heteroatoms. It's bonded to 3 H's and to a carbon. So no bonds to heteroatoms. It's at the alkane level. This carbon has 1 bond to a nitrogen, so we say is at the alcohol level. I tell you what, let's be a bit more, because it's going to get very confusing. So let's say blue is alkane. Let's say green is alcohol level. Let's say pink, good God, is aldehyde. Let's say brown is acid level, and then red, which is not a convincing red, that is this. Oh, where's black? Let's say black red is carbon dioxide. Okay? So these are the levels. So again, alkane level is 0 bonds to heteroatoms. So this carbon is at the alkane level because it has no bonds to a heteroatom. This carbon has 1 bond to a heteroatom, so it's at the alcohol level. This carbon has 1 bond to a heteroatom, it's also at the alcohol level. This carbon has 1, 2, 3 bonds to heteroatoms, so that's at the acid level. This carbon has 1 bond to a heteroatom, so that's at the alcohol level. This carbon also has 1 bond to heteroatom, that's also at the alcohol level. This carbon has 0 bonds to heteroatoms, so that's at the alkane level. This carbon has 2 bonds to heteroatoms, so that's at the aldehyde level. This carbon has 0 bonds to heteroatoms, so that's at the alcohol level. This carbon has 1, 2, 3 bonds to heteroatoms, so that's at the acid level. This carbon has 1, 2, 3, 4 bonds to heteroatoms, so that's at the carbon dioxide level. This carbon also has 1, 2, 3, 4 bonds to heteroatoms, that's also at the carbon dioxide level. So there are carbons that span the gamut from alkane level, these are the most reduced carbons. Then the alcohol level, 1 level up, and then aldehyde, then acid, and then carbon dioxide levels. So one of the questions you will often get is just identifying oxidation levels for the carbons. I could also, by the way, while I'm on this question, ask for hybridization states of the carbons. So that's sp3, 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 sp2, sp3, sp3, sp2, sp3, sp2, sp, because they've got 2 pi bonds, and it's also sp2. Okay, so what we're going to do is look at some calculations that are involved in redox, because we talked about very briefly a little while ago that redox chemistry is one of the most important frameworks for organic chemistry, in that when we look at the interconversion of organic compounds, when we look at organic reactions, which we will spend some time on, you look at organic reactions as one of sort of 3 major areas. One is carbon-carbon bond formation and breakage. One is what's called functional group interconversion. We'll get to these in more detail later on. But the third axis upon which you hang organic reactions is redox. We want to have a really good understanding of when redox happens and how much do we spend in terms of electrons in redox processes. So we want to look at a scenario in which, for example, let's say I ask you, what happens when I convert, let's say, this compound to this compound, and that compound to this compound, and then this compound maybe to this compound. Or if I convert this compound into this compound. This one into that one, for example. And I want to ask the question, well, which of these reactions, if any, is a redox reaction, right? In which of these reactions is my organic compound undergoing oxidation or reduction? Or for that matter, if I convert it into this compound. Well, the first thing I'm going to do is ask, well, where is chemistry happening? So if we go this way, let's go right, I have a carbon that is at the alcohol level of oxidation. Whatever reaction I carry out, and for now the reagents are not important, whatever reactions I carry out, I'm making this carbon now remains at the alcohol level. So this does not involve redox. I'm going to say no redox. So I start off with a carbon at the alcohol level, I end up with a carbon at the alcohol level. So there's been no redox. There's been a change in the group, but gone from Cl to OH, but the reaction does not involve redox. But what about here? Well, this carbon is at the alcohol level. This carbon is at the aldehyde level. So I've done an oxidation. I've gone from the alcohol level to the aldehyde level. This is an oxidation. So I can write oxidation in two ways. I can write O with a caret on top. That's the same as writing O in square brackets. So those are shorthand ways of representing oxidation. So if I want to indicate that I've done an oxidation, then I show O in square brackets or O with caret on top. What if I convert this compound to this one? Well, this carbon is at the aldehyde level, 2 bonds to heteroatoms. This carbon is at the aldehyde level, 2 bonds to heteroatoms. So this also is no redox. If I convert it into this compound, well, this carbon is at the aldehyde level, 2 bonds to heteroatoms. This carbon is at the alcohol level, 1 bond to heteroatom. So that is a reduction, which I write as either H in square brackets or H with a caret on top. Those are interchangeable operators. Going from here to here, this carbon is at the alcohol level, this carbon is at the aldehyde level, 2 bonds to heteroatoms. So this is also an oxidation. Now if I look at this one, and I ask you what's happening here, well, this compound contains 1 carbon at the alcohol level, but in the product, this is now at the alkane level. In this one, so that is actually reduction. I'm going from here to here, that's actually reduction. But this carbon is at the alkane level, and it goes now to the alcohol level in the product. So alcohol goes to alkane, at the same time alkane goes to alcohol. So overall, this does not involve redox. I'm going to say no redox. Although in reality, what I've done is I've done a reduction of this carbon, and then an oxidation of that one to the same extent. Because I've gone from alcohol, I'm moving between alcohol and alkane levels. So I can tell when there's been overall redox chemistry in a reaction just by looking at what groups are present in the starting material and what's present in the product. And that's very qualitative. What I want to be able to do is to do it in a more quantitative fashion. In other words, there are reagents that carry out oxidation. And I want to know how much of it do I need to carry out a given reaction. Right? There are species that are reducing agents, reductants, that carry out reductions. I want to know for a given reduction how much reagent do I need to carry out the reaction. So in order for us to do that, what we need to figure out is how many electrons are transferred as we go from one oxidation level to the next. So let's go ahead and start with the level. So let's say oxidation level. And we're going to pick, for example, CH4. And then we're going to do, and we did this when we were constructing the levels to begin with. We're going to go to the alcohol level. I don't quite have enough room here. So we're going to start with CH4. That's CH4. And then we're going to go to CH3OH. That's basically CH4O. So CH3OH is CH4O. Then we're going to go to the aldehyde level, which is CH2O. We're going to go to the acid level, which is CH2O2. And then we're going to go to this level, which is the carbonic acid, which essentially breaks down to carbon dioxide. But I'll leave it as this. I'll call it CH2O3. But this also will break down into CO2, right? So we'll have it there. So CO2. And so these are my oxidation levels, right? The alkane level, the alcohol level, the aldehyde level, the acid level, and the carbon dioxide level. What I'm going to do is I'm going to use oxidation numbers, which I know we said is dubious at best. But I'm going to ask for the oxidation number of each carbon, the oxidation number or state of each carbon. So, when we do that is we assume H's are +1. And there are 4 H's here, so that's +4, which means each carbon is -4. This is -4 for that carbon. Each O is -2. Each H is +1, so that's +4. So the oxidation number of this carbon is going to have to be -2. So -2 + 4, -2 is going to be 0. And all of these compounds are electrically neutral. So this carbon is at a -2 oxidation state. Each O is -2, each H is +1, and 2 of them, so that's +2. So the formal charge, the oxidation number of this carbon, is going to be 0. Each O is -2, and the 2 of them, that's -4. Each H is +1, and the 2 of those, that's +2, which means the carbon must be +2. Each O is -2, and the 3 of them, that's -6. The H is +1, and the 2 of those, so that's +2. So the carbon must be +4, which is the same as this one. Each O is -2, so that's -4. So the carbon has to be +4. So what this means is that as I toggle between adjacent oxidation levels, they represent a 2-electron process. As I go from the alkane level to the alcohol level, that represents a 2-electron loss in going from here to here. How do I go from -2, from -4 to -2? I lose 2 electrons. So going from here to here is a 2-electron loss. This is a 2-electron loss. In other words, it's a 2-electron oxidation. Because you know from Gen Chem, loss of electrons is oxidation. Whereas gain of electrons is reduction, right? Remember you would have learned in Gen Chem, you may have learned oil ring, right? Oxidation is loss of electrons, reduction is gain of electrons. So every time I go from an alkane level to the alcohol level, or the alcohol level to the aldehyde level, those represent processes that are 2 electron loss processes. Put another way, every time I gain a bond to a heteroatom, here I have no bonds to heteroatoms, here I have 1, here I have 2, here I have 3, here I have 4. Every time I gain a bond to a heteroatom, I'm losing 2 electrons, right? Because the 2 are the same. So as I go up this way, I'm losing 2 electrons from the electronic standpoint, but I'm also gaining 1 bond to a heteroatom. If I take a compound and I go from this compound to this compound, and I ask you, tell me what has happened. Well, you can tell me it's undergone oxidation. And how do I know that? Well, because at this point, this carbon has 1 bond to a heteroatom. This carbon has 1 bond to a heteroatom. Here it's got 3. Right? So as I gain bonds to heteroatoms, that represents oxidation. I can also say this compound has gained O's, which is a very loose and very low level definition. So it's oxidation because I've gained bonds to heteroatoms. If I were to ask you what's the extent of the oxidation, in other words, how many electrons did I lose in the process? Well, for every bond to a heteroatom that I gain, right? For every bond to a heteroatom that I gain, I lose 2 electrons. So I have moved from 1 bond to heteroatom to 3 bonds to heteroatoms. That represents a 4 electron loss. That's a 4 electron oxidation. Okay? If I take this compound and I convert it into this compound, and I ask you what has happened there, and you will tell me, well, I've certainly replaced the O's, but this carbon has 1, 2, 3 bonds to heteroatom. Here it's got 1, 2, 3 bonds to heteroatoms. That's not redox. So chemistry has happened. It's just not redox chemistry. And if I take that compound and I convert it into this one, and I ask you what happened, well, you will tell me I went from the acid level, with 3 bonds to heteroatoms, down to the aldehyde level, which is 2 bonds to heteroatoms. In the process, I have lost a bond to a heteroatom. That is reduction. To what extent? It is a 2 electron reduction. Because every time we move between adjacent oxidation levels, it's a 2 electron process. If I gain a bond to a heteroatom, that's 2 electrons I've lost. If I have lost a bond to a heteroatom, that means I've got reduced, that's a 2 electron gain. So I can describe whether processes are redox or not without being distracted by what atoms they're bonded to, whether they're Cls, Ns, sulfurs, Os is irrelevant. I can see through that and just count the bonds to heteroatoms. And again, what are heteroatoms? Any non-metal in an organic compound other than CNH. I can now say to what extent redox has occurred. Is it a 2 electron oxidation? Is it a 4 electron reduction? Based upon where the oxidation level is from the start compared to the finish. So this is going to become important in terms of using reducing and oxidizing agents. For example, it turns out that 2 of the most common oxidizing agents in chemistry, so in organic chemistry, are potassium permanganate, which you've met in Gen Chem. Potassium permanganate reacts under acidic conditions and forms manganese 2+. So potassium permanganate under acidic conditions can be reduced to form manganese 2+, but under basic conditions is reduced to MnO2, to manganese dioxide. what is happening? Well, we know that the oxidation number of K, because it's in group 1, that's potassium, right? That K is +1. Each O is -2. Each O is -2. And there are 4 of them, that's -8. Which means the oxidation number of manganese in potassium permanganate must be +7. In other words, this is manganese 7. Now we're all adults, we know that a metal can't have a charge of 7+, so this really is a formal charge. But this is manganese 7. Manganese 7 is a very deep purple color. Right? It's a very, very deep purple color. Under acidic conditions, manganese 7 gets reduced to manganese 2. Manganese 2 is a very, 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 very pale pink. So it is so pale pink, it looks as if it's colorless. And so if you're carrying out an oxidation using potassium permanganate, you know the reaction is going because the system goes from purple to colorless. Right? So under acidic conditions, potassium permanganate, when it carries out its reduction, gets decolorized because it goes from purple to colorless. Well, how many electrons are involved in that process? We're going from manganese 5 to manganese 2. That is a 5 electron gain. So the half reaction for this, is manganese 7 gains 5 electrons to become manganese 2+. And that's my purple to colorless. Under acidic conditions, right? This happens under acidic conditions. And of course, the manganese 7 is gaining 5 electrons, which means it is taking 5 electrons from somebody else. So that somebody else is then losing electrons and becoming oxidized in the process. So the manganese is getting reduced, that's the reduction part, and the other thing is getting oxidized, that's the oxidation part. So you have a redox occurring in tandem, because you can't have one without the other. So the manganese can't absorb electrons from space, it has to pick them up from somebody else. That somebody else is becoming oxidized. And while it's becoming oxidized, it's reducing the manganese 7. But what about here? Under basic conditions, manganese 7 gets reduced to manganese 2, to MnO2. And what happens here is each O is -2, that's -4, which means this Mn is +4. So this half reaction is manganese 7, now under basic conditions, is gaining 3 electrons to go from manganese 7 to manganese 4. Right? So manganese has a different oxidation profile. Potassium permanganate has a different oxidation profile under acidic conditions, where it is reduced to manganese 7, manganese 2, purple to colorless, and under basic conditions where it's reduced to manganese 4. MnO2 is a fine powdery black solid. So what you see when this reaction goes is the purple color is discharged and you're left with a fine black suspension. Okay. The other species that we're commonly going to use is potassium dichromate. And that can be written in lots of different ways, and this is usually acidified potassium dichromate. It can be written like this, or Cr2O7, 2- and H+, or sometimes as H2Cr2O7. There are lots of different ways, and they're all equivalent depictions. It is acidified dichromate, right? So dichromate. Regardless of which one I pick, let's pick the Cr2O7 2-. What is the oxidation number of the chromium in this species? Well, each O is -2, There's 7 of those, so that's minus 14. If there's an overall charge of 2 minus, then there must only be a plus 12 on these 2 chromiums, which means each chromium must be chromium 6 plus, or chromium 6. Chromium 6 is reduced into chromium 3. And that happens with a 3 electron gain. So chromium 6 gets reduced to chromium 3. This is a beautiful orange color, and this is a pretty green color. So what I see when I carry out oxidations using dichromate, or any version of chromium 6, because you can get chromium 6 either with dichromate or with CrO3, right? Or with K2CrO4. But the one you typically see is a dichromate. So all of these represent chromium 6. So chromium 6, so unlike manganese, which has different profiles under acidic and basic conditions, chromium 6 gets reduced to chromium 3. End of story. Okay. So let's see how we can put this together. So I'm going to give us a question where I'm going to ask, and again, I'm going to assume that you have this information written down somewhere, right? You copied it down and you're ready to use it, because we won't have it on the board anymore. So we're going to ask, how many equivalents of a given oxidizing agent, say, will we need to carry out a certain reaction? So for example, how many equivalents of KMNO4 are needed to oxidize this compound to this compound under acidic conditions. Okie dokie. So what this is essentially taking inventory of electrons, doing electron count. So what is the chemistry happening? When we are taking this organic compound and we are converting it into this organic compound. Okay? Is that oxidation, reduction, or neither? Well, the question is telling us we're oxidizing, so that's kind of a giveaway. But I'm going from one bond to a heteroatom, and this carbon, one bond to a heteroatom. This carbon now has 3 bonds to heteroatoms. As we increase the number of bonds to heteroatoms, we are moving up the oxidation ladder. This is at the alcohol level. So again, remember, it's alkane, alcohol, aldehyde, acid, and carbon dioxide. So we are going from the alcohol level to the acid level. We've gained 2 bonds to heteroatoms. That represents a 4 electron oxidation. So that is a 4 electron oxidation. Remember, if we go from between every level, as we toggle between levels, it's a 2 electron process. Here we're going from alcohol, 2 electrons to aldehyde, 2 electrons to acid, that's 4 electrons. Okay. What's happening, so this alcohol is going to be losing 4 electrons per molecule. What about the manganese? Well, the manganese, we know, is going from manganese 7 Just worked it out earlier. Under acidic conditions, that goes to manganese 2. That is a 5 electron process. From 7 to 2, I've gained 5 electrons. Plus 7 to plus 2 is a 5 electron gain. So the question is asking, how much manganese do I need for every alcohol molecule? And the easiest way to do that is just to swap these coefficients. In other words, 5, if I look at this, 5 of the alcohols will react with 4 of the manganese 7s, right? And I know that because 5 alcohols will collectively lose 20 electrons. If every one loses 4, 5 will lose 20. Each manganese gains 5. So 4 of them will gain 20 electrons. And this is what I want. I want the number of electrons lost and gained to be the same. They have to be. Because I can't manufacture electrons from space, and I can't dump electrons into space. Somebody has to give the electrons to somebody else. And that somebody else has to draw electrons from the first person. The amount I lose must equal the amount I gain. There must be electron balance in redox. So the easy way of looking at it is, I'm going to let this number go here, that number go there. And it looks like magic, but it's not. It makes sense. I want to make sure the number lost and gained is the same. So if 5 alcohols require 4 manganese 7s, then 1 alcohol, and how do I go from 5 to 1? I divide by 5. Therefore, I'm going to divide this side by 5 as well. So the 1 alcohol will need 4/5 of my manganese 7. 1 mole of the alcohols will need 0.8 moles of manganese 7. In other words, 0.8 equivalents. So if I have 1 mole of this, I'll need 0.8 moles of that. If I have half a mole, I'll need 0.4 moles of this. And so on and so on and so on. So the answer is I will need 0.8 moles of potassium permanganate to carry out this reaction. So what this means then is, if I know I have a mole of this, I go to the balance and I weigh out 0.8 moles of potassium permanganate. Now, the question could get a bit more exciting, and I will tell you, for example, suppose I had 35, suppose the question was, how many moles of permanganate do I need to oxidize 35 grams of this compound? Suppose it's at 35 grams. So how would I do that? Well, I have to convert the grams into moles. Right? All of these things are predicated on moles. That's easy enough. What is the molar mass of this compound? Well, the formula is C3, 1, 2, 3, H3, 5, 7, 8. Oh. So the molar mass of this is going to be 3 times 12 is 36, plus the 8, plus 16 for the O. These are atomic masses. So that's 12, 20, 3 is 4, is 5. So the molar mass of this compound is 50 grams per mole. The molar mass is 50 grams per mole. If I have 30 grams, you know the number of moles is the sample mass over the molar mass. So I will divide 35 grams by 50 grams per mole, and that works out to be, that's actually very nice, that works out to be 0.7 moles. Right? It's 0.7 moles. So, go going back to the calculation, if 1 mole of this compound needs 0.8 moles of permanganate, right? So 1 needs 0.8, then 0.7 moles will need 0.7 times 0.8 moles. That's going to be 0.56 moles of potassium permanganate. And the question could be even more tedious and say, what mass of potassium permanganate would I need to oxidize 35 grams of this compound? Well, that's easy. I know the number of moles I need is 0.56. I could work out the molar mass of potassium permanganate, right? Potassium is 39, manganese is 52. So manganese is 55, so it'd be 39 plus 55 plus 4 times 16 is 64. And this will be grams per mole for the molar mass. So that's, let's see, it's 39, so that's 89, 94, right? So 39, that's 89, 94, 98, 158. So it's 158 grams per mole is the molar mass. And if the question says what mass do I need, if it's 0.56 moles, I'll multiply 0.56 moles by the 158 grams per mole. So 0.56 moles times 158 grams per mole. So moles cancel out, and I have a number which is grams, right? So that would be about that would be about 83 grams. So that's 0.56 times 158. 88.5. So it'd be 88.48 grams. And this will be the question. I've got 2 sig figs. So I'm only allowed 2 sig figs in my answer to be 88 grams. So I'll need 88 grams of potassium permanganate to oxidize 35 grams of the alcohol. Right? So let's just be clear how this happened. We'll do some more. The question originally was, how many equivalents of potassium permanganate do I need to oxidize the alcohol to the carboxylic acid under acidic conditions? So I first want to figure out what has happened to the organic compound, right? And I said it went from 1 bond to a heteroatom, the carbon, from 1 bond to a heteroatom, because nothing happens here, so I'm going to ignore it. This carbon has undergone chemistry, 1 bond to a heteroatom to 3 bonds to a heteroatom. I have gained 2 bonds to heteroatoms. That represents a 4 electron oxidation, right? I'm going from alcohol, 2 electrons to acid. 4 electron loss oxidation. Okay, good. That's what happened to the organic. The reagent I'm using is potassium permanganate. That has manganese 7. Manganese 7 under acidic conditions gets reduced to manganese 2. That represents a 5 electron gain. So if I have something that requires 4 electrons mixed with something that releases 5 electrons, how much of each do I need? And I'm going to predicate this based upon the organic compound. The best way of doing it, and you could count it, but the best way is to say, have the 5 go here and the 4 go here, you swap them. And that works out because 5 of these will collectively lose 20 electrons, because each loses 4. 4 of these will collectively gain 5 electrons, because each one gains 5. Will collectively gain 20 electrons, because each one gains 5. And you want to make sure the number of electrons matches. So if 5 need 4, ratio and proportion, 1 will need 4 over 5, or 0.8. And that's where this question originally would have ended. I need 0.8 equivalents. The question may not be that straightforward. It may say, how many moles do I need for a certain mass of this? By the way, it can go one step further. I can give you a volume of this, because this compound is a liquid. So I can give you a certain volume of the liquid and tell you the density of it is, whatever, right? X grams per mil. Density is mass over volume. So the mass is going to be the density times the volume. So if I give you the volume of the alcohol and its density, well, I'm giving you access to the mass. Right? So you take that mass, you convert the mass into the number of moles, which is simply the sample mass, the 35 grams, over the molar mass, which I get from the molecular formula. That gives me the number of moles now of the compound. So in this particular case, it works out to be 0.7 moles. If 1 mole needs 0.8, 0.7 will need 0.7 times 8. And that's the number of moles of potassium permanganate I will need. The question could be icky and ask, what mass do you need? Well, that's fine. You multiply the sample mass by the molar mass, right? If I want little m, if the number of moles is sample mass over molar mass, then it stands to reason that the sample mass is the number of moles times the molar mass. The sample mass is the number of moles times the molar mass. Okay? Now imagine you're in a lab, and I'm telling you, look, I am giving you 35 grams of 1 propanol, that compound. Go and oxidize it. Well, how much permanganate are you going to use? You can use a gram? You can use 100 grams? I mean, how do you calculate that? And the answer is, you work it out. Right? You don't just add potassium permanganate and hope. I mean, you get fired for that. Because if you don't oxidize it all, right, that's not what your boss wanted. Your boss wanted you to oxidize it. At the same time, you don't want to pour in a ton of permanganate because you're wasting reagents. You've got to work it out. So I know if I'm going to use 35 grams of the alcohol, I need to have 88 grams of potassium permanganate. And I need this number, otherwise the reaction doesn't finish. I don't complete the reaction. Okay? Let's do another one. How many equivalents of potassium permanganate are needed to oxidize that compound? I'll use the same one. This time we're going to go to the alcohol, to the aldehyde. I'm going to do it under basic conditions. So we'll go from here to here under basic conditions. How do we do that? Well, what's happening to the organic compound? It's going from a compound having, a carbon having 1 bond to a heteroatom, one having 2. We're going from the alcohol level to the aldehyde level. Gaining 1 bond to heteroatom, that represents a 2-electron oxidation. The manganese under basic condition goes to manganese 4. That represents a 3-electron gain, manganese 7 to manganese 4. Swap my coefficients. It means 3 of the alcohols require 2 of the manganese 7s. Just to make sure, each alcohol loses 2, so these 3 will collectively lose 6. Each of these gains 3, therefore 2 of them will collectively gain 6 electrons. And it must be that way. Okay, so the number of electrons lost and gained is the same, because you can't manufacture electrons, nor can electrons simply blink out of existence. Well, if 3 alcohols need 2 permanganates, 1 alcohol will need 2/3 of the permanganate. Ratio and proportion. If Divide by 3, divide by 3. So the answer to this question is I will need 0.66 equivalents, 0.67 equivalents. The question could have asked, what mass of pyramid do I need to work on a certain mass of this? You do exactly the same thing. Take the mass you're given, convert it into the number of moles, and that number of moles, if it's X number of moles, you multiply it by 2/3 to get the number of moles of manganese 7. Let's do another one. How many equivalents of potassium dichromate are needed to oxidize, let's say, methanol, carbon dioxide? Now, this is where it's going to stop because this compound is only used under acidic conditions. How do we do that? Well, methanol is this compound, and it's going to carbon dioxide. Well, that's an oxidation. We're going from 1 bond to heteroatom to 4 bonds to heteroatom. So we've gained 3 bonds to heteroatom. Every time we do that, that's a 2 electron loss, right? So we go from the alcohol level, 2 electrons to the aldehyde, 2 electrons to the acid, 2 electrons to carbon dioxide. In other words, I'm doing this using 2 electrons, right? This using 2 electrons. This using 2 electrons. So collectively, this is a 6 electron loss. The dichromate, if you remember, is chromium 6. And that goes to chromium 3+, orange to green. That represents a 3 electron gain. But here's the trick, this one. Dichromate means there are 2 chromium 6s in this species. Each one will gain 3 electrons. So while every CR6 gains 3 electrons, because there are 2 chromium 6s, they will collectively gain 6 electrons to form 2 CR3+. So, how many equivalents of this do I need for every one of these? 1. 6 to 6. Right? So what this means, right, is that the methanol, right, so I'm just going to write it. 6 methanols will need 6 CR2O7s. In other words, 1 needs 1. So I simply need 1 equivalent of potassium dichromate to oxidize methanol to carbon dioxide. Let's add a little wrinkle to this. Let's say what mass of KMnO4 is needed to oxidize 45 cm cubed of this alcohol to this ketone under acidic conditions. Okay? So what mass of potassium permanganate do I need to oxidize that alcohol to that ketone under acidic conditions? So I'm going to have in my head what my roadmap is here. I need to understand the redox chemistry happening. That's at the core. What is happening from a redox perspective to each of these species? Well, I'm going from this compound to this compound. What is happening to it? Chemistry is happening here. This carbon is at the alcohol level, 1 bond to a heteroatom. That's at the aldehyde level, 2 bonds to a heteroatom. I'm moving between alcohol and aldehyde, that's a 2 electron loss. I am gaining 1 bond to a heteroatom, that's a 2 electron loss. So this is a 2 electron loss process. What is happening to the permanganate? Well, the permanganate is going from manganese 7. We are under acidic conditions, which you must know means it's going to manganese 2+. Let me just be very clear on that. I will not tell you in the exam, without penalty, I'll take away points if I have to, that manganese 7 goes to manganese 2 under acidic conditions. That's something you need to know. I will not tell you that manganese 7 goes to manganese 4 under basic conditions. Or if I say it goes from purple to colorless, that's me telling you 7 to 2. If I say there's a black precipitate, that's me telling you 7 to 4. So you must know that. Under acidic conditions, we go from manganese 7 to manganese 2. That's a 5 electron gain. Right? That means 5 of the alcohols will need 2 of the manganese 7s. Never hurts to double check. Each alcohol loses 2. Collectively, 5 will lose 10 electrons. Each manganese 7 gains 5. Collectively, 2 of them will gain 10 electrons. It must be that way. The number lost and gained must be the same. So it means then 1 alcohol will require 2/5 permanganate. In other words, it requires 0.4 equivalents of the permanganate. That's not what I asked you. The question was, what mass do I need for a certain volume of the alcohol? It's on that, I forgot to give you. But this is at the heart, this is the nucleus of the question. The rest of it now is furthest. Okay. Well, I then need to know, well, how many moles do I actually have? How many moles of the alcohol do I have? Well, the question tells you it's 45 mils that you have. I forgot to give you a density. I don't know what it is offhand. I'm going to say the density of the alcohol is equal to 0.987 grams per cm cubed. I'm just pulling that number out of the sky. Well, I need to know the number of moles that I have. To get the number of moles, I need the mass. So density is equal to mass over volume. Therefore, mass is equal to density times volume, which is equal to 0.987 grams per cm cubed times the 45 cm cubed. And that's equal to 42.3. I'm just guessing. So 0.987 times 45. Okay, way off. So that's 44.415 grams. Now, I'm really limited to 2 sig figs in these calculations. I'm going to carry 3 of them through, right, until I get to the end. So I'm going to go ahead and make this 44.4 grams.